Look around you. Everything that defines modern civilization, from the AI cluster powering ChatGPT to the $1,200 smartphone in your pocket, to the navigation systems inside an F-35 fighter jet, relies on one single physical element: silicon chips. We like to believe that the key to this multi-trillion-dollar digital economy resides in Silicon Valley, Austin, or Tokyo. We think tech giants like Apple, NVIDIA, and Microsoft control our digital future. They don't, because every single advanced microchip on Earth, 100% of the chips built at 5 nanometers, 3 nanometers, and beyond, must pass through one single machine built by one single company in a quiet town in the Netherlands called Veldhoven. That company is ASML. This is their flagship creation, the High-NA EUV lithography system. Price tag: over $350 million per machine. Weight: 150 metric tons, requiring 3 fully loaded Boeing 747 freighters just to ship a single unit. Complexity: composed of over 100,000 individual precision components. If ASML's factory in Veldhoven were to stop operating tomorrow, the global tech economy wouldn't just slow down, it would enter a forced blackout within 18 to 24 months. This isn't just business, it is the most critical single point of failure in human industrial history. How did a once obscure Dutch joint venture become an absolute monopoly with zero competitors? And what happens when an entire global market becomes hostage to a single $350 million engine? In classical economics, absolute monopolies are supposed to be impossible. If a business generates insane profit margins, free market competition dictates that rivals will inevitably enter the space, undercut prices, and erode market share. Yet, ASML stands as a terrifying exception to basic economic law. In the most advanced segment, extreme ultraviolet EUV lithography, ASML's market share isn't just dominant, it is absolute. Canon left the high-end race decades ago. Nikon, once the undisputed king of lithography in the 1980s, now holds a marginal sliver of the market. This total market domination translated directly to the stock exchange. Between 2014 and 2024, ASML's market capitalization exploded by over 1,000%, peaking at over $380 billion. It quietly surpassed European legacy titans like LVMH and Shell to become the most valuable technology enterprise in Europe. How did ASML avoid the wrath of antitrust regulators? Because they didn't buy out their competitors through predatory acquisitions. They simply out-engineered and outspent the entire world until everyone else quit. According to ASML's financial filings, ASML reinvests 14% to 15% of its total net revenue into research and development every single year. Between 2021 and 2025, their annual R&D budget scaled from 2.5 billion euros to well over 4.2 billion euros. To put that into perspective, if a well-funded competitor, or even a sovereign government, wanted to build a replacement for ASML from scratch today, they wouldn't just need $50 billion in capital. They would need to collapse 20 years of trial and error physics into a single afternoon. The economic barrier to entry isn't a wall, it's an ocean. To understand why this machine costs $350 million, you have to understand that ASML doesn't just build hardware, they manipulate the fundamental physics of light. Conventional lithography uses deep ultraviolet, DUV, light with wavelengths of 193 nanometers. But to print circuit patterns smaller than 7 nanometers, engineers needed light with a wavelength of just 13.5 nanometers, almost bordering on X-rays. There's a catch. 13.5 nanometer EUV light doesn't exist naturally in a usable form, and it is absorbed by almost everything, including glass, air, and oxygen. So, how does ASML generate this light inside the machine? First, a generator spits out 50,000 microscopic molten tin droplets per second, moving at over 200 miles per hour. Second, a high-power industrial laser strikes each individual tin droplet twice. The first laser blast flattens the droplet. The second vaporizes it into plasma at temperatures 40 times hotter than the surface of the sun. This plasma emits 13.5 nanometer EUV light, which is captured and focused into a beam. All of this happens 50,000 times every second in a strict vacuum chamber. Here is the counterintuitive economic secret of ASML. ASML only manufactures about 15% of the components inside its own machines. The remaining 85% is outsourced to an ultra-specialized network of thousands of global suppliers. ASML is not just a hardware maker, it is the master architect of a global capitalist organism. Consider Carl Zeiss SMT, the sole supplier of EUV high-precision mirror systems. The mirror surface must be smoothed down to the atomic level. If you scaled a Zeiss mirror up to the size of the entire United States, the largest bump on the surface would be less than 1 millimeter high. ASML holds a 24.9% equity stake in Carl Zeiss SMT to secure its strategic alignment. In 2012, ASML faced a massive financial existential crisis. The development costs for EUV were ballooning, and the company was running out of cash. Wall Street was skeptical. ASML's executive team came up with a bold, unprecedented financial deal: the Customer Co-Investment Program. They approached their three biggest potential customers, Intel, TSMC, and Samsung, and offered them a deal. Intel acquired a 15% stake in ASML and pledged €829 million in R&D funding. TSMC acquired a 5% stake and committed €276 million in R&D. Samsung acquired a 3% stake and committed €276 million in R&D. In total, ASML raised over €3.8 billion directly from the companies that would eventually buy their products. ASML effectively convinced its buyers to fund their own suppliers' high-risk R&D. Once EUV succeeded, these tech giants saw their equity stakes appreciate exponentially while securing priority access to the only machinery capable of making next-gen chips. To Wall Street, ASML isn't just an engineering marvel, it's a money-printing machine with a business model that defies typical hardware economics. Usually, manufacturing physical hardware involves high marginal costs, supply chain bottlenecks, and razor-thin profits. Look at typical hardware makers. Their gross margins hover around 20% to 30%. ASML, on the other hand, maintains gross margins between 50% and 53%, operating margins above 30%, and a return on equity often exceeding 45%. How does a company selling 150-ton steel machines achieve a 53% gross margin? The answer is simple: zero price elasticity of demand. When ASML increases the price of an EUV machine from $150 million to $200 million, or even $350 million for their High-NA models, TSMC or Intel cannot walk away. If you are building a $20 billion semiconductor fabrication plant, a machine without alternative options holds infinite pricing power. ASML sets the price, the market pays it. The semiconductor industry is notoriously cyclical. Booms are followed by devastating busts. Yet, ASML has insulated itself through an enormous buffer, the backlog. In recent fiscal years, ASML's net bookable orders backlog has consistently floated between €30 billion and €39 billion. This backlog represents roughly 1.5 to 2 full years of total annual revenue. Even if a sudden global recession hits and chipmakers freeze new equipment orders tomorrow, ASML's assembly lines in Veldhoven will remain at maximum capacity through the downturn. Furthermore, downstream market dynamics enforce this. TSMC, Samsung, and Intel spend a combined $70 billion to $90 billion annually in capital expenditure. Roughly 20% to 30% of that cash flows directly onto ASML's balance sheet. When you control the bottleneck of the modern economy, you don't just attract investors, you attract foreign policy hawks, intelligence agencies, and economic warfare. ASML is a Dutch company based in the European Union. So why does the United States have the authority to decide where ASML can and cannot ship its machines? The lever is the U.S. Export Administration Regulations and the Foreign Direct Product Rule. Because ASML's machines incorporate key technologies developed on U.S. soil, such as light source intellectual property from Cymer in San Diego and software algorithms running on American components, U.S. law dictates that any machine containing more than a minimal threshold of U.S. technology is subject to Washington's export control licenses. Through the International Wassenaar Arrangement and direct diplomatic pressure, the U.S. government pressured the Dutch government to revoke and deny export licenses for ASML's advanced EUV systems to specific overseas markets starting in 2019, later expanding restrictions to cover high-end DUV immersion systems like the TwinScan NXT 2000 series. This geopolitical crossfire placed ASML's management in an uncomfortable position. In 2023, high-end immersion DUV sales spiked in certain restricted markets as buyers rushed to stockpile equipment before sanctions fully tightened, briefly accounting for up to 40% of ASML's quarterly revenue. When domestic political movements in the Netherlands began pushing for anti-immigration laws and tighter foreign worker visas, former ASML CEO Peter Wennink delivered an ultimatum to the Dutch government. If the Netherlands limits our ability to hire top global engineering talent and stifles our growth, ASML will expand outside the Netherlands. The response from the Dutch cabinet was swift and desperate. Codenamed Project Beethoven, the Dutch government scrambled to approve a €2.5 billion infrastructure package specifically to keep ASML rooted in Veldhoven, funding local roads, housing, and technical universities. ASML had become bigger than the state itself. No monopoly lasts forever, as ASML pushes into the uncharted territory of sub-2 nanometer manufacturing. Its biggest challenge might not come from regulators. It might come from simple financial mathematics. ASML's newest crown jewel is the High-NA EUV. By increasing the numerical aperture from 0.33 to 0.55, this machine can etch tiny transistor features down to 2 nanometers and below in a single exposure pass. But the physics comes with an astronomical price tag: unit cost, over $350 million to $400 million per machine. Fabs must redesign their entire cleanroom ceilings because the machine is significantly taller and heavier. For chipmakers like TSMC, the return on investment equation is becoming stressed. If the cost per transistor stops dropping, the economic law that drove the tech revolution, Moore's Law, breaks down. If chipmakers decide that multi-patterning using older, cheaper EUV or DUV machines yields better margins than buying $350 million high-NA units, ASML's growth engine could face a structural ceiling. At the same time, the industry is searching for workarounds to bypass physical lithography altogether. Competitors like Canon are pushing nano-imprint lithography systems, which physically stamp patterns onto the silicon wafer like a mechanical press, promising to reduce equipment costs by up to 60% and power consumption by 90%. Additionally, companies are increasingly combining smaller, cheaper chiplets using 3D stacking techniques. ASML is a testament to what human engineering can achieve when global capital, precision physics, and international collaboration align. They took an impossible physical problem and turned it into the most profitable monopoly in modern tech history. But as each new machine crosses the $350 million mark, the fundamental question facing the semiconductor industry is no longer just whether we can push physics further, it's whether the market can afford the bill. Has ASML pushed the price of lithography beyond the point of economic returns? Or will High-NA EUV remain the undisputed engine of the AI revolution for the next decade? Let me know your thoughts on ASML's financial and technological future in the comments below. Thanks for watching, and I'll see you in the next video.